Welcome to C Programming for Everybody. My name is Charles Severance, and this is my reading of the 1978 C programming book written by Brian Kernighan and Ritchie. At times, I add my own interpretation of the material from a historical perspective. Chapter 1, a tutorial introduction. Let us begin with a quick introduction to C. Our aim is to show the essential elements of the language in real programs, but without getting bogged down in details, formal rules, and exceptions. At this point, we are not trying to be complete or even precise. We want you to get as quickly as possible to the point where you can write useful programs. And to do that, we have to concentrate on the basics: variables and constants, arithmetic, control flow, functions, and the rudiments of input and output. We are quite intentionally leaving out of this chapter features of C which are of vital importance for writing bigger programs. These include pointers, structures, and most of C's rich set of operators, several control flow statements, and a myriad of details. This approach has its drawbacks, of course. Most notable is that the complete story on any particular language feature is not found in a single place. The tutorial, by being brief, may also mislead. And because they cannot use the full power of C, the examples are not as concise and elegant as they might be. We have tried to minimize these effects, but be warned. Another drawback is that later chapters will necessarily repeat some of this chapter. In any case, experienced programmers should be able to extrapolate from the material in this chapter to their own programming needs. Beginners should supplement it by writing small, similar programs of their own. Both groups can use it as a framework on which to hang the more detailed descriptions that begin in Chapter 2. 1.1. Getting started. The only way to learn a new programming language is by writing programs in it. The first program to write is the same for all languages. Print the words, "Hello, world." This is the basic hurdle. To leap over it, you have to be able to create the program text somewhere, compile it successfully, load it, run it, and find out where your output went. With these mechanical details mastered, everything else is comparatively easy. In traditional C, the program to print "Hello World" is main, open parenthesis, close parenthesis, open curly brace, printf, parenthesis, double quote, hello, comma, space world, \n, double quote. Close parenthesis, semicolon, close curly brace. The modern minimal version of this program needs a bit more syntax. We add a single line at the beginning. #include space left angle brackets stdio.h right angle bracket pound include stdio.h. We have to add that line for the modern program. Back to the book. Just how to run this program depends on the system that you're using. As a specific example, on the Unix operating system, you must create the source program in a file whose name ends in .c, such as hello.c, and then you compile it with the command cc space hello.c. If you haven't botched anything, such as omitting a character or misspelling something, the compilation will proceed silently and make an executable file called a.out. Running that by the command a.out will produce hello, world as its output. On other systems, the rules will be different. Check with a local expert. On modern systems, we use the GCC compiler with the -ANSI option to accept the legacy syntax of C. So we use GCC space -ANSI space hello.c. And to run the resulting a.out file, you need to prepend the local directory because most shell configurations do not include the current path in the paths to search for applications. So you need to write /a.out. Now for some explanations about the program itself. A C program, whatever its size, consists of one or more functions which specify the actual computing operations that are to be done. C functions are similar to functions and subroutines of a Fortran program or the procedures of PL1, Pascal, etc. In our example, main is such a function. Normally, you are at liberty to give functions whatever names you like, but main is a special name. Your program begins executing at the beginning of main. This means every program must have a main somewhere. Main will usually invoke other functions to perform its job, some coming from the same program and others from libraries of previously written functions. One method of communicating data between functions is by arguments. The parentheses following the function name surround the argument list. Here, main is a function of no arguments, indicated by open parenthesis, close parenthesis. The curly braces enclose the statements that make up the function. They're analogous to the do end of PL1 or the begin end of Algol or Pascal and so on. A function is invoked by naming it, followed by a parenthesized list of arguments. There is no call statement as there is in Fortran or PL1. The parentheses must be present even if there are no arguments. In the above text, the authors were making connections to the popular general-purpose programming languages of the time. When the book was written, it was not all assured that C and C-like languages would ever evolve past writing high-performance applications like operating system kernels and device drivers. By comparing C to these more general-purpose languages, the authors are trying to plant the seed that C could have value as a general-purpose language. Back to the text. The line that says printf parenthesis double quote hello comma space world backslash n double quote close parenthesis semicolon is a function call, which calls a function named printf with the argument hello world. Printf is a library function which prints the output to the terminal unless some other destination is specified. In this case, it prints the string of characters that make up its argument. Any sequence of any number of characters enclosed in double quotes is called a character string or string constant. For the moment, our only use of the character strings will be as arguments to printf and other functions. The sequence \n in the string is C notation for the new line character, which when printed advances the terminal to the left margin on the next line. If you leave out the \n, a worthwhile experiment by the way, you'll find that your output is not terminated by a line feed. The only way to get a new line character into the printf's argument is with \n. If you try to break it into two lines, like printf quote hello world, and then just hit the return, double quote, close parenthesis, semicolon on a new line, the C compiler will print out unfriendly diagnostics about missing quotes. Printf never supplies a new line automatically, so multiple calls can be used to build up an output line in stages. Our first program could have just as well been written as main open parenthesis, close parenthesis, open curly brace, printf quote hello quote semicolon, printf quote world quote semicolon, printf \n semicolon, and then on a sixth line close curly brace, and it would have produced the identical output. Note that \n represents only a single character. An escape sequence like \n provides a general and extensible mechanism for representing hard to get or invisible characters. Among the others that C provides are \t for tab, \b for backspace, double quote for double quote, and \/ for the backslash itself. 1.2, page 8, variables and arithmetic. The next program prints the following table of Fahrenheit temperatures and their centigrade or Celsius equivalents. Using the formula, C equals parenthesis 5 divided by 9, close parenthesis, F minus 32. The table contains Fahrenheit of 0, Celsius of negative 17.8, Fahrenheit of 20, Celsius of negative 6.7, Fahrenheit of 40, Celsius of 4.4, and so forth. Here is the program itself. For reference, this program is on page 29 of the textbook. So it starts with pound include stdio.h to include the standard library. Then it has a comment that says print the Fahrenheit Celsius table for f equals 0, 20, dot, 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 300. Close comment. Main, open parenthesis, close parenthesis, open curly brace, int, lower, upper, step, semicolon, float, var, Celsius, lower equals 0, semicolon, followed by a comment, upper equals 300, semicolon, followed by a comment, step equals 20, semicolon, followed by a comment, var equals lower, and then while, open parenthesis, var less than or equal to upper, close parenthesis, open curly brace, Celsius equals parenthesis 5.0 slash 9.0, close parenthesis, asterisk, open parenthesis, var minus 32.0, close parenthesis, semicolon. Then a printf statement, printf, open parenthesis, double quote, percent 4.0f space percent 6.1f backslash n, close quote, var, Celsius, close parenthesis, semicolon. Var equals var plus step, and then a closing curly brace to finish the while statement, and then a closing curly brace to finish the main statement. The first two lines, slash star print Fahrenheit to Celsius table for f equals 0, 20, dot, 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 300, star slash are a comment, which in this case explains briefly what the program does. Any characters between slash star and star slash are ignored by the compiler. They may be used to freely make the program easier to understand. Comments may appear anywhere a blank or new line can. In C, all variables must be declared before use, usually at the beginning of a function, before any executable statements. If you forget a declaration, you will get a diagnostic from the compiler. A declaration consists of a type and a list of variables that have that type, as in int, lower, upper, step, semicolon, float, var, Celsius, semicolon. The type int implies that the variables listed are integers. Float stands for floating point, i.e., numbers which may have a fractional part. The precision of both int and float depends on the particular machine that you are using. On the PDP-11, for instance, an int is a 16-bit signed number. That is, one that lies between negative 32,768 and positive 32,767. A float number is a 32-bit quantity which amounts to about 7 significant digits, with a magnitude of about 10 to the minus 38 and 10 to the plus 38. Chapter 2 lists the sizes for other machines. I would note that the 1970s was a time of transition in the amount of memory installed in computers. The C language int type was 16 bits in the older but more generally available computers like the PDP-11. C could be used to write programs like the Unix operating system that made efficient use of available memory. In particular, the 1978 version of C did not require that computers support 32-bit integers. But 32,768 is a pretty small number. The size of an integer affected the maximum size of arrays and strings. A lot of early C programs used the long type to get at least a 32-bit integer capable of representing numbers up to about 2 billion. In modern computers and databases, we tend to choose between 32-bit and 64-bit integers. Back to the text. C provides several other basic data types besides int and float. Char is a character, a single byte. Short is a short integer. Long is a long integer, and double is a double precision floating point. The size of these objects are also machine dependent, and details are in Chapter 2. There are also arrays, structures, and unions of these basic types, and pointers to them and functions that return them all of which we will meet in due course. The actual computation in our temperature conversion program begins with the assignments lower equals 0, upper equals 300, step equals 20, far equals lower, all ending with semicolon. These set the variables to their starting values. Individual statements are terminated by semicolons. Each line of the table is computed in the same way, so we use a loop which repeats once per line. This is the purpose of the while statement. While, parenthesis, far less than or equal upper, close parenthesis, open curly brace, then the body of the loop, and then close curly brace. The condition in the parentheses is tested. If it is true, i.e. far is less than or equal to upper, the body of the loop, all of the statements included between the open curly brace and the closed curly brace are executed. Then the condition is retested. If true, the body is executed again. When the test becomes false, i.e. far exceeds upper, the loop ends and execution continues at the statement that follows the loop. There are no further statements in the program, so it terminates. The body of a while loop can be one or more statements enclosed in braces, as the temperature converter, or a single statement without braces, as in while, open parenthesis, I less than j, close parenthesis, I equals 2 times I, semicolon. In either case, the statements controlled by the while are indented by one tab stop, so you can see at a glance what statements are inside the loop. The indentation emphasizes the logical structure of the program. Although C is quite permissive about statement positioning, proper indentation and the use of white space are critical in making programs easy for people to read. We recommend writing only one statement per line and usually leaving blanks around operators. The position of the braces is less important. We have chosen one of the several popular styles. Pick a style that suits you and then use it consistently. I would add that with these words, the authors triggered a great debate about how to best indent code and use curly braces that continues to this day. The indentation style used in this book is often referred to as the K&R style. It tends to put open braces at the end of statements like if and while to keep code more compact in terms of the number of lines of code. The best advice is not to debate at all. When you modify someone else's code, just imitate the style that they used when they wrote their code. Back to the text. Most of the work gets done in the body of the loop. The Celsius temperature is computed and assigned to the Celsius variable by the statement Celsius equals, open parenthesis, 5.0 slash 9.0, close parenthesis, asterisk, open parenthesis, far minus 32.0, close parenthesis, semicolon. The reason for using 5.0 slash 9.0 instead of the simpler looking 5 slash 9 is that in C, as in many other languages, integer division truncates so that any fractional part is discarded. Thus, 5 slash 9 is 0. And of course, so would then all the temperatures be 0. A decimal point in a constant indicates that it is floating point, so that 5.0 over 9.0 is 0.555 repeating, which is what we want. We also wrote 32.0 instead of 32, even though since far is a float, 32 would automatically be converted to float before the subtraction. But as a matter of style, it's wise to write floating point constants with explicit decimal points, even when they have integral values. It emphasizes their floating point nature for human readers and ensures the compiler will see things the way you do as well. I would note that for those of you familiar with Python, before Python 3, integer division truncated and returned an integer, just like C. In Python 3, one of the major improvements was that the division of two integers performed the division operation in floating point and returns a floating point result. C and Python 2 made the choice because of efficiency. Integer division with truncation, especially for 16-bit numbers, was quite fast in the 1970s computers compared to floating point division that kept the fractional part intact. Early PDP-11 computers did integer division in hardware, while all floating point was done with loops and functions, so it was far slower. If you wanted to write fast code in the 1970s, you avoided floating point numbers except for special situations. Modern computers usually do 64-bit floating point operations almost at the same speed as integer division, so we don't need to allow programmers to avoid using floating point computations in their code. The detailed rules for when integers are converted to floating point are in Chapter 2. For now, notice that the assignment far equals lower semicolon and the test while far less than or equals upper both work as expected. The int is converted to a float before the operation is done. This example also shows a bit more of how printf works. Printf is actually a general-purpose format conversion function, which we will describe completely in Chapter 7. Its first argument is a string of characters to be printed, with each % sign indicating where one of the other, second, third, etc. arguments is to be substituted and what form it is to be printed in. For instance, in the statement, printf, parenthesis, double quote, %4.0f space %6.1f, \n, double quote, comma far, comma Celsius, the conversion specification %4.0f says that a floating point number is to be printed in a space at least 4 characters wide with no digits after the decimal point. %6.1f describes another number to occupy at least 6 spaces with 1 digit after the decimal point, analogous to the F6.1 of Fortran or the F parentheses 6, 1 of PL1. Parts of a specification may be omitted. %6f says that the number is to be at least 6 characters wide. %.2f requests 2 places after the decimal point, but the width is not constrained. And merely %f says to print the number itself as floating point. Printf also recognizes %d for decimal integers, %o for octal, %x for hexadecimal, and %c for characters, and %s for a character string, and % for the % itself. Each % construction in the first argument of printf is paired with its corresponding second, third, etc. argument. They must line up properly by number and type, or else you'll get meaningless answers. By the way, printf is not part of the C language. There is no input or output defined in C itself. There is nothing magic about printf. It's just a useful function, which is part of the standard library of routines that are normally accessible to C programs. In order to concentrate on C itself, we won't talk much about I/O until Chapter 7. In particular, we'll defer formatted input until then. If you have to input numbers, read the discussion of the function scanf in Chapter 7, Section 7.4. Scanf is much like printf, except that it reads input instead of writing output. The balance between building a feature into the language itself and providing it as a function in a library is something that computer language designers struggle with many years later. For example, in Python 2, print was a language element. In Python 3, one of the non-upwards compatible and somewhat unpopular changes was changing print to be a function. Many programmers feel that a print statement is a more elegant way to express printing, but from a compiler and language design perspective, a function call with a variable number of parameters is seen as technically more elegant and flexible. With Kernighan and Ritchie focused on keeping everything small and portable, they opted to keep all input-output functionality in libraries. The syntax is a little more complex, but given how computing has changed in the past 30 years, it is the right choice. Section 1.3, the for statement. As you might expect, there are plenty of different ways to write a program. Let's try a variation on the temperature converter. This is sample code is on page 11 of the textbook. Pound sign include less than stdio.h greater than. Main, open parenthesis, close parenthesis, open curly brace. Int far, that is F-A-H-R, semicolon. For, open parenthesis, far equals 0, semicolon. Far less than or equal to 300, semicolon. Far equals far plus 20, close parenthesis. Printf, open parenthesis, double quote, %4d space %6.1f backslash n, close quote. Comma, far, comma, open parenthesis 5.0 slash 9.0, close parenthesis, asterisk, open parenthesis, far minus 32, close parenthesis, semicolon. This code produces the same answers as the one before, but it certainly looks different. One major change is the elimination of most of the variables. Only far, F-A-H-R, remains as an int to show the %d conversion in printf. The lower and upper limits of the step size appear only as constants in the for statement itself. The for is a new construction, and the expression that computes the Celsius temperature now appears as the third argument of printf instead of in a separate assignment statement. This last change is an instance of a quite general rule in C. In any context where it is permissible to use the value of a variable of some type, you can use an expression of that type. Since the third argument of printf has to be a floating point value to match the %6.1f, any floating point expression can occur there. The for itself is a loop, a generalization of while. If you compare it to the earlier while, its operation should be clear. It contains three parts separated by semicolons. The first part, far equals 0, is done once before the loop proper is entered. The second part is the test or condition that controls the loop, far less than or equal to 300. This condition is evaluated. If it is true, the body of a loop, in this case a single printf, is executed, then the reinitialization step, far equals far plus 20, is done and the condition is reevaluated. The loop terminates when the condition becomes false. As with the while, the body of the loop can be a single statement or a group of statements enclosed in braces. The initialization and reinitialization parts can be any single expression. The choice between while and for is arbitrary and should be based on what seems clearer. The for is usually appropriate for loops in which the initialization and reinitialization are single statements and logically related, since it is more compact than while and keeps the loop control statements together in one place. I would note that the syntax of the for and while loop is a feature of C and derived C-like languages. In modern languages, we tend to have two kinds of loop structures, determinate and indeterminate. The for and the while loop structures in C are both indeterminate because you must read them closely to make sure they are properly constructed and, for example, are not unintentionally infinite loops. An example of a determinate loop is the for each loop in PHP or the for loop in Python. The semantics of both of these loops is to iterate all the elements in a collection. But since collections are never infinite, you can be assured that these determinate loops will not run forever. Section 1.4, Symbolic Constants. A final observation before we leave temperature conversion. It's a bad practice to bury magic numbers or magic constants like 320 or 320 in a program. They convey little information to someone who might read the program later, and they're hard to change in a systematic way. Fortunately, C provides a way to avoid such magic numbers. With the # define construction at the beginning of a program, we can define a symbolic name or symbolic constant to be a particular string of characters. Thereafter, the compiler will replace all unquoted occurrences of the name by the corresponding string. The replacement for the name can actually be any text at all. It's not related to numbers. So this is a sample code on page 13 of the text. # include less than stdio.h greater than. Next line, pound define space lower space 0. Next line, pound define space upper space 300. Pound define space step space 20. For these pound sign statements, I would note that they have to start in the first column. The rest of this sample code is the code itself. Main open parenthesis, close parenthesis, open curly brace, int far, F-A-H-R, for open parenthesis, far equals uppercase lower, semicolon, far less than or equal to uppercase upper, semicolon, far equals far plus uppercase step. And then the same print statement. Printf, open parenthesis, double quote, %4d space %6.1f \n, quote, comma, far, comma, %5.0/9.0, close parenthesis, asterisk, open parenthesis, far -32, close parenthesis, semicolon, and then to end the program, close curly brace. The quantities, uppercase lower, uppercase upper, and uppercase step, are constants, so they do not appear in declarations. Symbolic names are commonly written in uppercase, so they can be readily distinguished from lowercase variable names. Notice that there is no semicolon at the end of a pound define statement. Since the whole line after the defined name is substituted, there would be too many semicolons in the for. Section 1.5, a collection of useful programs. We are now going to consider a family of related programs for doing simple operations on character data. You will find that many programs are just expanded versions of the prototypes we discuss here. Character input and output. The standard library provides functions for reading and writing a character at a time. Getchar fetches the next input character each time it is called and returns the character as its value. That is, after c equals getchar, open parenthesis, close parenthesis, the variable c contains the next character of input. These characters normally come from the terminal or keyboard, but that need not concern us until Chapter 7. The function putchar, open parenthesis, c, close parenthesis, is the complement of getchar. Putchar, open parenthesis, c, close parenthesis, prints the content of the variable c on some output medium, again usually the terminal or screen. Calls to putchar and printf may be interleaved. The output will appear in the order in which the calls are made. As with printf, there is nothing special about getchar and putchar. They are not part of the C language, but they are universally available. Once again, I would note that the authors are making the case that the syntax of the language should not include syntax for input-output operations, but instead call library functions. Keeping the compiler small and easy to port new systems was important to the creators of C. And even if something like putchar was part of the language syntax, it would be translated at runtime to call a function. Programming languages from the 1960s tended to have a small set of use cases: read some input, run some calculation, and then write some output. So it seemed like a few language elements would be sufficient to describe all programs. But as programs started to make network connections, draw buttons on a screen, or respond to API calls over the network, it would have been difficult to keep expanding the core language syntax for each new use case. But it was extremely natural to add new libraries to languages like C with functions to call to accomplish these new use cases. File copying. Given getchar and putchar, you can write a surprising amount of useful code without knowing anything more about input-output. The simplest example is a program which copies its input to its output, one character at a time. In outline, here's what we do. Get a character. While the character is not the end of file signal, output the character we just read and then get a new character. Converting this into C gives us the sample code on page 14 of the textbook. Pound includes stdio.h, main open parenthesis, close parenthesis, open curly brace, int C, semicolon. C equals getchar, open parenthesis, close parenthesis, semicolon, while C not equal EOF, uppercase EOF, close parenthesis, open curly brace, put char C, C equals get char semicolon, close parenthesis, close curly brace. The relational operator exclamation equals means not equal to. The main problem is detecting the end of the input. By convention, getchar returns the value, which is not a valid character when it encounters the end of input. In this way, programs can detect when they did not get a character and they've actually simply run out of input. The only complication, which is a serious nuisance, is that there are two conventions in common use about what that end of file value really is. We have deferred this issue by using the symbolic name EOF, capital EOF, for the value, whatever it might be. In practice, EOF will be either -1 or 0, so the program must be preceded by the appropriate #define EOF -1 or #define EOF 0 to work properly. By using the symbolic constant EOF to represent the value that getchar returns when the end of file occurs, we are assured that only one thing in the program depends on the specific value, numeric value of EOF. I would note, most of that is incorrect. Modern C compilers actually define EOF in the stdio.h include file. So you never define EOF in your code. In modern C, the value of EOF is -1. You should just include stdio.h and use predefined EOF constant to check for end of file. The nuisance of different values for EOF was resolved shortly after 1978. Continuing with the text. We also declare C to be an int, not a char, so that it can hold the value which getchar returns. As we'll see in Chapter 2, the value is actually an int because it must be capable of representing end of file in addition to all possible characters. So the program for copying could actually be written more concisely by experienced C programmers. In C, any assignment, such as C equals getchar open parenthesis close parenthesis, can be used in an expression. Its value is simply the residual value being assigned to the left-hand side. If the assignment of a character to the variable C is put inside the test part of a while statement, the file copy program can be written as shown in the example code on page 15 of the textbook. #include stdio.h, main open parenthesis close parenthesis, open curly brace, int space C semicolon. While open parenthesis, C equals getchar open parenthesis, close parenthesis, not equal EOF, close parenthesis, put char C, parenthesis, C, close parenthesis, semicolon, close curly brace. The program gets a character, assigns it to C, and then tests whether the character was the end of file signal. If it was not, the body of the while is executed, printing the character. The while then repeats. When the end of input is finally reached, the while terminates, and so does main. This version centralizes the input. There is now only one call to getchar and shrinks the program. Nesting an assignment is a test of one of the places where C permits a valuable conciseness. It is possible to get carried away and create impenetrable code, though that is a tendency we will try to curb. It's important to recognize that the parentheses around the assignment within the conditional are really necessary. The precedence of exclamation equal, not equals, is higher than that of equals, the assignment operator, which means that in absence of parentheses, the relational test, exclamation equals, would be done before the assignment, equals. So the statement C equals getchar parenthesis, open parenthesis, close parenthesis, not equal EOF is equivalent to C equals getchar, is equivalent to C equals open parenthesis, getchar, open parenthesis, close parenthesis, not equal EOF, close parenthesis. This has the undesired effect of setting. It is important to recognize that the parentheses around the assignment within the conditional are really necessary. the precedence of exclamation equals is higher than that of equals, which means that in the absence of parentheses, the relational test not equals would be done before the assignment. So the statement C equals getchar not equal EOF is equivalent to C equals open parenthesis getchar not equal EOF close parenthesis. This has the undesired effect of setting C to 0 or 1 depending on whether or not the call of getchar encountered the end of file. More on this in Chapter 2. The next program counts characters. It is a small elaboration of the copy program. This sample code is on page 16 of the textbook. Pound include stdio.h, main, open parenthesis, close parenthesis, open curly brace, long, nc semicolon, nc equals 0 semicolon, while, open parenthesis, getchar, open parenthesis, close parenthesis, exclamation equal EOF, plus plus nc semicolon, printf, double quote, %ld backslash n, double quote, comma, nc, parenthesis, semicolon, close curly brace. The statement plus plus nc semicolon shows a new operator, plus plus, which means increment by 1. You could write nc equals nc plus 1, but plus plus nc is more concise and often more efficient. There is a corresponding operator, minus minus, to decrement by 1. The operators plus plus and minus minus can either be prefix operators, plus plus C, nc, or postfix, nc plus plus. These two forms have different values and expressions, as will be shown in Chapter 2. But plus plus nc and nc plus plus both increment nc. For the moment, we'll stick to the prefix form. The character counting program accumulates its count in a long variable instead of an int. On a PDP-11, the maximum value of an int is 32,767, and it would take relatively little input to overflow that counter if it were declared as an int. In Honeywell and IBM C, long and int are synonymous and much larger. The conversion specification %ld signals to printf that the corresponding argument is a long integer. As a note, we again see another reference to the fact that the number of bits of the int type is in transition in 1978. The older PDP-11 used a 16-bit integer to save limited memory on a small, almost obsolete computer, while later computers from IBM and Honeywell have already switched to their int type to be 32 bits. This allowed code originally written for the PDP-11, like Unix or even the C compiler, to be recompiled on the IBM or Honeywell with very few changes. To cope with bigger numbers, you can use a double, which is a double-length float. We will also use a for statement instead of a while to illustrate an alternate way to write a while loop. This code is the second sample code on page 16 of the textbook. Pound include stdio.h, main, open parenthesis, close parenthesis, open curly brace, double, nc, semicolon. For, open parenthesis, nc equals 0, semicolon, getchar, open parenthesis, close parenthesis, not equal EOF, semicolon, plus plus nc, close parenthesis, and then a semicolon. The semicolon in this case is an empty statement because there's nothing in the body of the for loop. And at the end we say printf, double quote, %.0f backslash n, double quote, comma, nc, close parenthesis, semicolon, close curly bracket. Printf uses %f for both float and double. %.0f suppresses printing of the non-existent fraction part. The body of the for loop here is empty because all the work is done in the test and reinitialization parts of the for loop. But the grammatical rules of C require that a for statement have a body. The isolated semicolon, technically a null statement, is there to satisfy that syntax requirement. We put it on a separate line to make it more visible. Before we leave the character counting program, observe that if the input contains no characters, the while or for test fails on the very first call to getchar, so that the loop program produces 0, the right answer. This is an important observation. One of the nice things about while and for is they are tested at the top of the loop before proceeding with the body. If there is nothing to do, nothing is done, even if that means never going through the loop body. Programs should act intelligently when handed input like no characters. The while and the for statements help ensure that they do reasonable things with boundary conditions. Line counting. The next program counts lines in its input. Input lines are assumed to be terminated by the new line character \n that has been carefully appended to every line written out. This is sample code on line 17 of the textbook. Pound includes stdio.h. Main, open parenthesis, close parenthesis, open curly brace. Int, c, comma, nl, semicolon. nl equals 0, semicolon. While, open parenthesis, c equals getchar, open parenthesis, close parenthesis, not equal EOF, close parenthesis. If, open parenthesis, c, double equals, single quote, \n, single quote, close parenthesis, plus, nl, semicolon. Printf, double quote, %d, \n, double quote, comma, nl, close parenthesis, semicolon, close curly brace. The body of the while loop now consists of an if, which in turn controls the increment ++nl. The if statement tests its parenthesized condition, and if true, does the statement or group of statements inside braces that follow. We have again indented to show what is controlled by what. The double equal sign is the C notation for is equal to, like Fortran's .eq. This symbol is used to distinguish the equality test, the question being asked, from the single equal sign used for assignment. Since assignment is about twice as frequently used as equality testing in typical C programs, it's appropriate that the operator be half as long. A single character can be written between single quotes to produce a value equal to the numerical value of the character in the machine's character set. This is called a character constant. So for example, single quote A, single quote is a character constant. In the ASCII character set, its value is 65, the internal representation of the character A. Of course, single quote A, single quote is to be preferred over 65. Its meaning is obvious, and it is independent of a particular character set. These escape sequences that are used in character strings are also legal and character constants. So in tests and arithmetic expressions, single quote \n, single quote, stands for the value of a new line character. You should note carefully that single quote \n is a single character, and in expressions is equivalent to a single integer. On the other hand, double quote \n double quote is a character string which happens to contain only one character. The topics of strings versus characters is discussed further in Chapter 2. The numeric values that are shown for characters are using the ASCII character set. The character sets in the 1970s were quite intricate. Most were 8 bits long to conserve computer memory and only support 100 or so Latin-like characters. This is why early programming languages use special characters like asterisk and curly brace in their syntax very carefully. They needed to choose characters that were commonly available on computer keyboards from different manufacturers. Modern programming languages like Python 3 and Ruby store internal string values using the Unicode character set, so they are all able to represent all the characters in all languages around the world. Modern languages tend to represent 8-bit values in the range from 0 to 256 using a byte or similar type. Python 2 strings were stored as 8-bit bytes, and Python 3 strings are stored as 32-bit Unicode characters. Moving to Unicode was a major effort in the Python 2 to Python 3 transition. Word counting. The fourth in our series of useful programs counts lines, words, and characters. with a loose definition that a word is any sequence of characters that does not contain a blank, a tab, or a new line. This is a very bare bones version of the Unix utility WC. This example is on page 18 in the textbook. Pound include stdio.h. Pound define yes, 1. Pound define no, 0. Main, open parenthesis, close parenthesis, open curly brace. Int c, nl, nw, nc, inword. Inword equals no. nl equals nw equals nc equals 0. While open parenthesis, c equals getchar, not equal to EOF, open curly brace, plus plus nc. If, parenthesis, c double equals, quote, backslash n, quote, parenthesis, plus plus nl. If, open parenthesis, c double equals, single quote, space, single quote, double vertical bar, c double equals, single quote, backslash n, single quote, double vertical bar, c equals, single quote, backslash t, single quote, close parenthesis, inward equals no. Else if, open parenthesis, inward equal no, close parenthesis, open curly brace, inward equals yes, semicolon, plus plus nw, semicolon, close curly brace, printf, open parenthesis, double quote, %d, space, %d, space, %d, backslash n, double quote, comma, nl, comma, nw, comma, nc, close curly brace. Every time the program encounters the first character of a word, it counts it. The variable inward records whether the program is currently in a word or not. Initially, it is not in a word, which is assigned the value no. We prefer the symbolic constants yes and no to the literal values 1 and 0 because they make the program more readable. Of course, in a program as tiny as this, it makes little difference, but in larger programs, the increase of clarity is well worth the modest effort to write it this way, to make it more readable. You will also find that it's easier to make changes to programs where numbers appear only as symbolic constants. The line nl equals nw equals nc equals 0 sets all three variables to 0. This is not a special case, but a consequence of the fact that an assignment has a value and assignments associate right to left. It's really as if we had written nc equals open parenthesis nl equals open parenthesis nw equals 0 close parenthesis, semicolon. The operator double vertical bar means or. So the line if open parenthesis c double equals single quote space single quote vertical bar c double equals single quote backslash n single quote double vertical bar c double equals quote backslash t quote parenthesis says if c is a blank or c is a new line or c is a tab. The escape sequence backslash t is a visible representation of the tab character. There's a corresponding operator which is double ampersand for and. Expressions connected by double ampersand or double vertical bar are evaluated left to right, and it is guaranteed that the evaluation will stop as soon as the truth or falsehood for the overall expression is known. Thus, if C contains a blank, there is no need to test whether it contains a new line or tab. So these tests are not made. This isn't particularly important here, but is very significant in more complicated situations, as we will soon see. I would note that the double vertical bar and double ampersand are the norm for Boolean operators in C-like languages. When a new language was being designed, it was really easy to just adopt the C convention for logical operators because, while they may seem cryptic, millions of software developers were already familiar with the operators. In this way, the relationship between C and C-like languages is like the relationship between Latin and Romance languages, including English. Back to the text. The example also shows the C else statement, which specifies an alternative action to be done if the condition part of an if statement is false. The general form is if, open parenthesis, expression, close parenthesis, statement 1, else statement 2. One and only one of the two statements associated with an if then else is done. If the expression is true, statement 1 is executed. If not, statement 2 is executed. Each statement can actually be, in fact, quite complicated. In the word count problem, the one after the else is an if that controls two statements in braces. Section 1.6, Arrays. Understanding the capabilities and limitations of C arrays is one of the most important topics in our historical look at the C programming language. Most importantly, the number of elements in an array declaration must be a constant at compile time, and the size of an array cannot be adjusted using an array declaration while the program's running. This inability to automatically resize C arrays as data is added leads to a class of security flaws that are generally referred to as buffer overflow, where a program reads more data in that can fit into an array and is tricked to overriding other data or code and compromising an application. Later in this book, we will create dynamic array-like structures in C using pointers and the standard library calloc function. Python has support for non-dynamic arrays, buffers. Python buffers are generally not used except for programmers writing library code that talks to low-level code written in a language other than Python, or talking to operating system things like Linux. The more commonly used Python list and dictionary structures can change their sizes automatically as elements are added and deleted at runtime. Java has support for non-dynamic arrays like C, which are given a length at the moment they are created, and the array length cannot be increased nor decreased without making a new array and copying all the elements from the first to the second array. Java does provide list and map structures that automatically adjust their length as data is added or removed. Java has a class called ArrayList, which can be dynamically extended but provides array-like linear access. It is a list internally, but it can be used like an array externally. The underlying technique that is used to implement language structures like Python's list is dynamic memory allocation and a linked list structure. Linked lists are one of the most important data structures in all of computer science. We will cover dynamic allocation and implementing data structures in C in Chapter 6. For now, we will merely examine the syntax of C arrays, but keep in mind that allocating an array in C is very different than creating a list in Python. Back to the text. Let us write a program to count the number of occurrences of each digit of white space characters, blank tab and new line, and all other characters. This is an artificial problem to solve, but it permits us to illustrate several aspects of C in one program. There are 12 categories of input, so it is convenient to use an array to hold the number of occurrences of each digit rather than 10 individual variables. Actually 12 individual variables. Here is one version of the program on page 21 in the textbook. And I would note that as these programs get larger and larger, it is harder and harder for you to just listen to me read them, and you have to go look at them in the textbook. So I recommend that you go check out the textbook in page 20 and find this actual code. Pound include stdio.h. Main, open parenthesis, close parenthesis, open curly brace. Int C, comma I, comma n white, comma n other, semicolon. Int n digit, open square bracket, 10, close square bracket, semicolon. N white equals n other equals 0, semicolon. 4, open parenthesis, I equals 0, semicolon. I less than 10, semicolon. Plus plus I, close parenthesis, n digit, open square bracket, I, close square bracket, equals 0, semicolon. Now we're going to have a loop to read all of our input, while double open parentheses, C equals getchar, open parenthesis, close parenthesis, and another close parenthesis, not equal EOF, close parenthesis. If, open parenthesis, C greater than or equal to, single quote, 0, single quote, double ampersand, C less than or equal, single quote, 9, single quote, close parenthesis, plus plus, n digit, open square bracket, C minus single quote 0, single quote, close square bracket, semicolon. Else if, open parenthesis, C double equals space, quote, space, quote, or double vertical bar, C double equals single quote backslash n single quote, double vertical bar, C double equals single quote backslash T single quote, close parenthesis, plus plus n white, semicolon. Else plus plus n other. That if statement was a sort of a 3-branch if, checking to see if we were doing a digit, a white space character, or some other character. At the end of the while loop, or not the end of the while loop, and so we say printf, parenthesis, double quote, digits equals, double quote, close parenthesis, semicolon. Now we'll note in this that there is no new line. So we can have these printfs kind of concatenate outward without going to a separate line. For parenthesis, I equals 0, semicolon, I less than 10, semicolon, plus plus I, close parenthesis. Printf, double quote, space, percent, D, double quote, comma, n digit, open square bracket, I, close square bracket, close parenthesis, semicolon. Printf, open parenthesis, double quote, backslash n, white space equals, percent D, comma, other equals, percent D, backslash n, double quote, comma, n white, comma, n other, close parenthesis, semicolon, close curly brace. Let's go through the code. The declaration int, n digit, open square bracket, 10, close square bracket, semicolon, declares n digit to be an array of 10 integers. Array of subscripts always start as 0 in C rather than 1 as in Fortran or PL1, so the elements are n digit sub 0, n digit sub 1, dot dot dot, n digit sub 9. Square brackets are the sub. This is reflected in the for loops which initialize and print the array. A subscript can be any integer expression, which of course includes integer variables like I and integer constants. This particular program relies heavily on the properties of character representation of the digits. For example, if C greater than or equal to single quote 0, single quote, double ampersand, C less than or equal to single quote 9, single quote, close parenthesis, determines whether it's a digit. That is, if the numeric value of the digit and the numeric value of the digit is C minus double quote 0, double quote. This only works if double quote 0, double quote 1, etc. are positive and increasing order. And there's nothing but digits between 0 and 9. Fortunately, this is true for all conventional character sets. By definition, arithmetic involving chars and ints converts everything to int before proceeding. So char variables and constants are essentially identical to ints in arithmetic contexts. This is quite natural and convenient. For example, C minus single quote 0, single quote is an integer expression that gives us a value between 0 and 9, an integer value between 0 and 9, corresponding to the character quote 0 quote 2 quote 9 quote stored in C, and is thus a valid subscript for the 10-element array n digit. The decision as to whether the character is a digit, a white space, or something else is made by the sequence if, open parenthesis, C greater than or equal to, quote 0 quote, double ampersand, C less than or equal, quote 0 quote, quote 9 quote, close parenthesis, plus plus n digit, open square bracket, C minus, quote 0 quote, close bracket, semicolon. Else if C double equals single quote or C double equals single quote backslash n, or C double equals single quote backslash T, plus plus and white, else plus plus and other. The pattern, if in parentheses condition statement, else if parentheses condition statement, else statement occurs frequently in programs as a way to express a multi-way decision. The code is simply read from the top of the until the bottom until some condition is satisfied. At that point, the corresponding statement part is executed and the entire construction is finished. Of course, statement can be several statements enclosed in braces. If none of the conditions are satisfied, the statement after the final else is executed if present. If the final else and statement are omitted, as in the word count program, no action takes place. There can be an arbitrary number of else if condition statements, groups between the initial if and the final else. As a matter of style, it is advisable to format this construction, as we have shown, with proper indentation, so that long decisions do not march off the right side of the page. The switch statement, to be discussed in Chapter 3, provides another way to write multi-way branching that is particularly suitable when the condition being tested is simply whether some integer or character expression matches one of a set of constants. For contrast, we will present a switch version of this program in Chapter 3. Functions. In C, a function is equivalent to a subroutine or function in Fortran, or a procedure in PL1, Pascal, etc. A function provides a convenient way to encapsulate some computation in a black box, which can then be used without worrying about its innards. Functions are really the only way to cope with the potential complexity of large programs. With properly designed functions, it is possible to ignore how a job gets done. Knowing what is done is sufficient. C is designed to make the use of functions easy, convenient, and efficient. You will often see a function only a few lines long called only once, just because it clarifies some piece of code. So far, we have used functions like printf, getchar, and putchar that have been provided for us. Now it's time to write a few of our own. Since C has no exponentiation operator like the double asterisk of Fortran or PL1, let us illustrate the mechanics of function definition by writing a function, power, open parenthesis, m, comma, n, close parenthesis, to raise an integer into a positive power n. That is, the value of power, parenthesis 2 comma 5 is 32. This function certainly doesn't do the whole job of exponentiation since it only handles positive powers of small integers, but it is best to confuse only one issue at a time. Here is the function power and a main program to exercise it so you can see the whole structure at once. This sample code is on page 23 of the textbook. Pound include stdio.h. Main, open curly brace, int I, semicolon. For parenthesis I equals 0, semicolon, I less than 10, semicolon, plus plus I, close parenthesis. Printf, double quote, %d space, %d space, %d backslash n, double quote, comma. I, comma, power, open parenthesis 2, comma, I, close parenthesis, comma, power, open parenthesis, -3, comma, I, close parenthesis, semicolon, close curly brace, the end of the main. Now we begin the function. Power, open parenthesis, x, comma, n, close parenthesis. Int, x, comma, n, semicolon, open curly brace. Int, I, comma, p. P equals 1. For, open parenthesis, I equals 1, semicolon, I less than or equal to n, semicolon, plus plus I. P equals p times x, semicolon. Return, open parenthesis, p, close parenthesis, semicolon, close curly brace. Each function has the same form. Function name, open parenthesis, argument list, if any, followed by argument declarations, if any, followed by the body of the function, which includes declarations and statements. The functions can appear in either order and in one source file or two. If, of course, the source file appears in two files, you will have to say more to compile and load it than if all appears in one. but that's an operating system matter, not a language attribute. For the moment, we'll just assume that both functions are in the same file, so whatever you learned about C programs, running them will not change. The function power is called twice in the line printf, open parenthesis, double quote, %d space %d space %d \n, double quote, comma I, comma power, open parenthesis, 2 comma I, close parenthesis, comma power, open parenthesis, -3, comma I, close parenthesis, close parenthesis. Each call passes 2 arguments to the power function, which each time returns an integer to be formatted and printed. In the expression, power, open parenthesis, 2 comma I, is just an integer as 2 and I are. Not all functions produce an integer value, and we'll take this up in more detail in Chapter 4. In power, the arguments have to be declared appropriately so their types are known before the beginning of the body of the function. This is done by the line int x, n, semicolon that follows the function name. The argument declarations go between the argument list and the opening left brace. Each declaration is terminated by a semicolon. The names used for power and for its arguments are purely local to power and not accessible to any other functions. Other routines can use the same names for their variables without conflict. This is also true of the variables I and p within the function. The I in power is unrelated to the I in main. The value that power computes is returned to main by the return statement, which is just as in PL1. Any expression must occur within the parentheses. A function need not return a value. A return statement with no expression causes control but no useful value to be returned to the caller, as does falling off the end of a function by reaching the terminating right curly brace. Section 1.8, Arguments, Call by Value. One aspect of C function, which may be unfamiliar to programmers who are used to other languages, particularly Fortran and PL1, in C, all function arguments are passed by value. This means that the called function is given the values of its arguments in temporary variables, actually on a stack, rather than their addresses. This leads to some different properties than are seen with call by reference languages like Fortran and PL1, in which the called routine has handled the address of the argument, not its value. It may seem strange that the authors are calling so much attention to the fact that function arguments are passed call by value in the very first chapter. Most modern programming languages like Python, PHP, or Java pass single value arguments by value by default. And to pass in an argument by reference, you need to do something special, like adding the ampersand in the function declaration in PHP. Passing by reference was the norm before C, and passing by value was the norm after C. Since modern languages were deeply influenced by and often written in C, passing by value is the norm for modern languages. It's nice because it isolates the data in the calling code from the called code. So the called code can't easily mess with its arguments, either intentionally or by mistake, and create an unexpected side effect and possibly a bug or security flaw in the calling code. It was a bit of work to make pass by value work in C. C implements a call stack where a bit of memory is automatically allocated at each function call, and C makes a copy of the values in the calling code to pass them into the called code in a way that the calling code can see the values and change their local copies without affecting the values in the calling code. The same call stack that made it possible for C function arguments to be passed by value also made it possible for a function to call itself recursively. Fortran functions could not be called recursively until the 1990 version of Fortran. If you know your Python, you know that simple variables like integers and strings are passed by value, while structured data like dictionaries and lists are passed by reference, i.e., the called function can modify its arguments. We will later see this in C as well. Talking about call stacks, recursive functions, and the fact that arrays and structured are called by reference is jumping ahead somewhat. So for now, let's just remember the author's point. that normal values like integers and floats are passed by value in C. Back to the text. The main distinction is that in C, the called function cannot alter a variable in the calling function. It can only alter its private temporary copy. Call by value is an asset, however, not a liability. It usually leads to more compact programs with fewer extraneous variables, because arguments can be treated as conveniently initialized local variables in the called routine. For example, here is a version of power which makes use of this fact. This code is on page 24 of the text. Power, open parenthesis, x, comma, n, close parenthesis. Int, x, comma, n, semicolon, open curly brace. Int, I, comma, p, semicolon. For, open parenthesis, p equals 1 semicolon, n greater than 0 semicolon, minus minus n, close parenthesis. P equals p times x, semicolon, return, open parenthesis, p, close parenthesis, semicolon, close curly brace. The argument n is used as a temporary variable and is counted down until it becomes 0. There is no longer a need for the variable I, as in the previous example. Whatever is done to n inside the power function has no effect on the argument that power was originally called with. When necessary, it is possible to arrange for a function to modify the variable in the calling routine. The caller must provide the address of their variable to be set, technically a pointer to the variable, and the called function must declare the argument to be a pointer and reference the actual variable indirectly through it. We will cover this in detail in Chapter 5. When the name of an array is used as an argument, the value passed to the function is actually the location or address of the beginning of the array. There is no copying of the elements in the array. By subscripting this value, the function can access and alter any element of the array in the calling code. This is the topic of the next section. Now, I would recommend that you're careful looking at the code samples in the rest of this chapter. Recall that in C, array sizes do not grow and shrink dynamically at all after they're allocated. The authors statically allocate character arrays capable of handling up to 1,000 characters long. Their code works, but it is somewhat brittle. So look at the next two sections as examples of C syntax with many important concepts about character strings stored as arrays and calling patterns when passing arrays to functions as parameters, but not exactly the best practice when handling dynamically sized data. Back to the text. Probably the most common type of array in C is an array of characters. To illustrate the use of character arrays and functions to manipulate them, let's write a program that reads a set of lines and prints the longest. The basic outline is simple enough. While there's another line, if it's longer than the previous longest, save it and its length, and then at the very end, print the longest line. The outline makes it clear that the program divides naturally into pieces. One piece gets a new line, another checks it, another saves it, and then the rest controls the process. Since things divide so nicely, it would be well to write them that way too. Accordingly, let's write first a separate function called getLine to fetch the next line of input. This is a generalization of getchar. To make the function useful in other contexts, we'll try to make it as flexible as possible. At the minimum, getLine has to return a signal about possible end of file. A more general useful design would be to return the length of the line, or 0 if the end of file is encountered. 0 is never a valid line length since every line has at least one character. Even a line containing only a new line has length 1. I would note that here in Chapter 1, we have changed the book's original use of the function name getLine to get_line in the code examples because it conflicts with the stdio.h that defines getLine as a library function. In this chapter, the authors are providing examples around function naming and linking. In later chapters, code samples will simply use the built-in getLine without an underscore to read an input. When we find a line that is longer than the previous longest, it must be saved somewhere. This suggests a second function, copy, to copy the new line to a safe place. Finally, we need a main program to control getLine and copy. Here is the result. The sample code for this is on page 26. And it's a bit long, so you might want to take a look at the sample code in a browser. Pound include stdio.h. Pound define max line 1000. Main, open paren, close paren, open curly brace, int len semicolon, which is the current line length, int max semicolon, which is the maximum length we've seen so far, char line, open square bracket, max line, close square bracket, semicolon. A character array, that's the current input line, and then char save, open square bracket, max line, close square bracket, semicolon, which is a character array that has the longest line where we're going to save it. Onto the code. Max equals 0, while open parenthesis, len equals getLine, open parenthesis, line, comma, max line, close parenthesis, greater than 0. If len is greater than max, open curly brace, max equals len to save it, and then copy, line, comma, save, close curly brace. If open parenthesis, max greater than 0, i.e. there was a line, printf, open parenthesis, double quote, %s, double quote, comma, save, close curly brace to end the main program. Now we're in the first function. GetLine, open parenthesis, s, comma, lim, close parenthesis. Char, s, open bracket, close bracket, semicolon. Since it's being passed in as an argument, we don't need to know the length of it. And the next argument is int lim semicolon. So getLine takes a character array of unknown length and a limit that tells us the length of the character array. Open curly brace, int c comma I semicolon. 4, open parenthesis, I equals 0 semicolon. I less than lim minus 1, double ampersand, parenthesis, c equals getchar, open parenthesis, close parenthesis, not equal EOF, and, double ampersand, c not equal, single quote, backslash n, single quote, semicolon, plus I. And in the body of the loop, it's s, open square bracket, I, close square bracket, equals c. From now on, I'll read that s sub I equals c. At the end of the loop, we say if, open parenthesis, c double equals, single quote, backslash n, single quote, close parenthesis, open curly brace, s sub I equals c plus I, close curly brace. S sub I equals, quote, backslash 0, quote, semicolon, return, open parenthesis, I, close parenthesis, semicolon, close curly brace. And that's the end of the getLine function. And now we're on to the copy function. Copy, open parenthesis, S1, S2, close parenthesis. The purpose of this function is to copy S1 to S2, assume that S2 is big enough. The declaration is char S1, open square bracket, close square bracket, comma, S2, open square bracket, close square bracket. As a note, these arrays have a size. We just don't know what they are, and we hope that they're large enough. The body of the copy function starts with open curly brace, int I semicolon, I equals 0, while open parenthesis, S2 sub I equals S1 sub I, close parenthesis, not equal, single quote, backslash 0, single quote, plus I, close curly brace to end the copy function. Main and getLine communicate both through a pair of arguments and a returned value. In getLine, the arguments are declared by the lines char s open square bracket, close square bracket, semicolon, int lim semicolon, which specify that the first argument is an array of unknown length and the second is an integer. The length of the array S is not specified in getLine since it's determined in main. GetLine uses return to send a value back to the caller, just as the function power did. Some functions return a useful value. Others, like copy, are only used for their effect and return no value. GetLine puts the character \0, the null character whose integer value is 0, at the end of the array it's creating to mark the end of the string of characters. This convention is also used by the C compiler. When a string constant like double quote HELLO \n double quote is written in a C program, the compiler creates an array of characters containing the characters of the string and adds a \0 at the end to terminate it so that functions such as printf can detect the end. So that would lead to an array that has HELLO \n\0. So it's a 5-character array with a new line, which is a 6th character, and then \0, which is an actual character. Again, we don't know, the arrays don't know their length, and so you use the \0 as the indicator of the end of a string. The %s format specification in printf expects a string represented in exactly this form. If you examine copy, you will discover that it too relies on the fact that its input argument s1 is terminated by \0, and it copies this character, \0, into the argument, output argument s2. All of this implies that \0 is not part of normal text. It's merely a marker. It is worth mentioning in passing that even a program as small as this one presents some sticky design problems. For example, what should main do if it encounters a line which is bigger than its limit? GetLine works properly in that it stops collecting when the array is full, even if no new line has been seen. By testing the length in the last character returned, main can determine whether the line was too long, then cope with it as it wishes. In the interests of brevity, we have ignored this issue. There's also no way for a user of getLine function to know in advance how long an input line might be, so getLine checks for overflow. On the other hand, a user of the copy function already knows or should be able to find out how big the strings are, so we have chosen not to add error checking to it. Section 1.10, Scope, External Variables. The variables in main, line, save, etc. are private or local to main. Because they are declared within main, no other function can have direct access to them. The same is true of the variables in the other functions. For example, the variable I in getLine is unrelated to the I in copy. Each local variable in a routine comes into existence only when a function is called and disappears when the function is exited. It is for this reason that such variables are usually known as automatic variables, following terminology in other languages. We'll use the term automatic henceforth to refer to these dynamic local variables. Chapter 4 discusses the static storage class in which local variables do retain their values between function invocations. Because automatic variables come and go with function invocation, they do not retain their values from one call to the next and must be explicitly set upon each entry. If they are not set, they will contain garbage. As an alternative to automatic variables, it is possible to define variables which are external to all functions, that is, global variables which can be accessed by name by any function that cares to. This function is rather like Fortran common or PL1 external. Because external variables are globally accessible, they can be used instead of arguments to communicate data between functions. Furthermore, because external variables remain in existence permanently rather than appearing and disappearing as functions are called and exited, they retain their values even after the functions that set them are done. An external variable has to be defined outside of any function. This allocates actual storage for it. The function also must be declared in each function that wants to access it. This may be done either by an explicit extern declaration or implicitly by context. To make the discussion concrete, let's rewrite the longest line program with line, save, and max as external variables. This requires changing the calls, declarations, and bodies of all three functions. This sample code is on page 29 of the textbook, and it's pretty long, but I'll read it for you. Pound include stdio.h. Pound define max line 1000. And we're still outside of main. Char line, open bracket max line, close bracket, semicolon. Char save, open bracket max line, semicolon. Int max semicolon. Those are our three global variables. Starting the main open paren, close paren, open curly brace. Int len, extern int max. So we're saying that this is an integer, but it's also not to be allocated inside of main. Extern char save, open square bracket, close square bracket. The length of the save array is defined above, so we don't need to define it here. Max equals 0, semicolon, while double parenthesis len, double left parenthesis len equals get line, parenthesis, greater than 0, parenthesis. If parenthesis len greater than max, open curly brace, max equals len, copy, open parenthesis, no parenthesis, semicolon, no parameters to copy, because it's going to simply talk to the global variables, close curly brace. After the loop finishes, we say if, open parenthesis, max greater than 0, then printf, open parenthesis, double quote, %s, double quote, comma, save, close parenthesis, semicolon, close curly brace, and that is the end of the main. So now we have the getLine function, which is specialized to deal with external variables. Okay. So we start getLine, open parenthesis, close parenthesis, no parameters, open curly brace, int, c, I, semicolon. These are local variables. Extern char line, open curly brace, close curly brace, semicolon. This is our reference inside of getLine to the global variable line. For open parenthesis, I equals 0, semicolon, I less than max line minus 1. Max line minus 1, max line is a predefined constant at compile time. For I less than max line minus 1, double ampersand, parenthesis, C equals getchar, open parenthesis, close parenthesis, not equal EOF, double ampersand, i.e. and, C not equal single quote \n, single quote semicolon, plus I. Line sub I equals C. That's the for loop that in effect reads characters one at a time and puts them in line. But after the for loop, we say if, open parenthesis, C double equals single quote \n, single quote, close parenthesis, open curly brace, line sub I equals C plus I, close curly brace. This ensures that we append the new line to the function. Line sub I equals single quote \0 \, that's semicolon. That's the string termination character. Return I. Return open parenthesis I, close parenthesis. This is the length that getLine is returning. And then close curly brace to end the getLine function. And then we have the copy function. And again, it takes no parameters. Copy, open parenthesis, close parenthesis, curly brace, int I, extern, char, line, open bracket, close bracket, comma, save, open bracket, close bracket, semicolon. I equals 0, while, parenthesis, open parenthesis, save sub I equals line sub I, close parenthesis, is not equal, quote, \0, quote, ++ I. Close curly brace for copy. So the external variables in main, getLine, and copy are defined by the very first lines in the example above, outside of main, which state their type and cause storage to be allocated for them. Syntactically, external definitions are just like the declarations we used previously, but because they occur outside of any function, including outside the main function, the variables are external. Before a function can use or access an external variable, the name of the variable must be made known to the function. One way to do this is to write an extern declaration in the function. The declaration is the same as before except for the added keyword extern. In certain circumstances, the extern declaration can be omitted. If the external definition of the variable occurs in the same source file before it's used in a particular function, then there's no need for an extern declaration in the function. The extern declarations in main and getLine and copy are thus redundant. In fact, common practice is to place all definition of all external variables at the beginning of the source file and then omit all extern declarations. If the program is in several source files and a variable is defined in, say, file 1 and used in file 2, then an extern declaration is needed in file 2 to connect the two occurrences of the variables. This topic is discussed at length in Chapter 4. You should note that we are using the words declaration and definition very carefully when we refer to external variables in this section. Definition refers to the place where the variable is actually created or assigned storage. Declaration refers to places where the nature of the variable is stated but no storage is allocated. By the way, there is a tendency to make everything in sight an extern variable because it appears to simplify things. Argument lists are short and variables are always there when you want them, but external variables are always there also when you don't want them. The style of coding is fraught with peril since it leads to programs whose data connections are not at all obvious. Variables can be changed in unexpected and even inadvertent ways, and the program is hard to modify when it becomes necessary. The second version of the longest line program is inferior to the first, partly because of these reasons, and partly because it destroys the generality of two quite useful functions by hardwiring them into the names of the variables they will manipulate. Section 1.11, Summary. At this point, we have covered what might be called the conventional core of C. With this handful of building blocks, it's possible to write useful programs of considerable size. And it's probably a good idea if you paused long enough to do so. The exercises that follow are intended to give you suggestions for programs of somewhat greater complexity than the ones presented in this chapter. After you have this much C under control, it will be well worth your effort to read on, for the features covered in the next few chapters are where the power and expressiveness of the language begin to become apparent. This work is based on the 1978 C programming book written by Brian W. Kernighan and Dennis M. Ritchie. The book is copyright all rights reserved by AT&T, but is being used in this work under fair use because of the book's historical and scholarly significance, its lack of ability, and lack of an accessible version of the book. The book is augmented in places to help understand its rightful place in historical context amidst the major changes of the 1970s and 1980s as a computer science evolved from a hardware-first vendor-centered approach to a software-centered approach where portable operating systems and applications written in C could run on any hardware. This is not the ideal book to learn the C programming language because the 1978 edition does not reflect the modern C language. Using an obsolete book gives us an opportunity to take students back in time and understand how the C language was evolving as it laid the groundwork for a future with portable applications.